Myself, Dr. R Keshavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the topic on the EPR and luminescence properties of Mn2 plus manganese 2 plus dope Boro phosphate glasses. So this is the one of the topic in the main topic of the laser glass spectroscopy. So last and previous session was discussed on EPR and spectral properties of chromium 3 plus ions in borate glasses. So last lesson we discussed on the chromium 3 plus ions in borate glasses. So that are the outline of the topic is the introduction and evidence of mixed alkali effect, experimental methods, research and discussion, and conclusion. Today I am going to discuss about the EPR and luminescence properties of Mn2 plus doped Boro phosphate glasses. So outline of the today talk is on the introduction and evidence of mixed alkali effect, experimental methods or techniques, results and discussion, and conclusion on the EPR and luminescence properties of Mn2 plus doped Boro phosphate glasses. So first one is introduction. Glass is one of the most important material in modern information and communication and laser technologies. The drastically growing market for television screens and data displays need glass with a variety of coating on its surface. Glass is extremely against environmental attacks. This is one of the important property of the glass material. So glasses are roughly speaking liquids that do not crystallize at even very low temperature also. It do not crystallize at low temperature also. That is the glass material. So glasses are very versatile material due to the fact that they can be easily doped with the transition metal ions as well as rare earth ions or lanthanide ions. So in our study we are going to dope with transition metal ions. In last session we discussed about the chromium 3 plus ion doped with borate glasses. Today topic is the same transition metal ions only, manganese Mn2 plus ions doped with Boro phosphate glasses, that we are going to discuss in the present study. So introduction continuation, the ionic conductivity of alkali borophosphate glasses has a nonlinear dependence on composition when borate replaces phosphate glasses, and this behavior has been called the mixed glass former effect. So recently borophosphate glasses have been developed for a variety of applications due to their unique properties such as low dispersion, relatively high refractive index, etc. compared to borate and telluride glass. These are the important properties in the case of borophosphate glasses. So one thing is unique properties, low dispersion, relatively high refractive index when compared to the borate and telluride glasses. So that is the one of the important unique properties of the borophosphate glasses. So that is this one. Next, presence of phosphate glasses, that means P2O5. Here we are discussing about the borophosphate. So borate P2O3 and additionally you are adding phosphorus pentoxide P2O5. That extends the, so whenever this phosphate glasses doped within borate glasses, that will be the extends the ultraviolet UV region and reduce the infrared transmission. So it will be increase the UV region, at the same time reduce the infrared transmission. It also reduce the chemical resistance of the glass. So these are the important properties or unique properties of the borophosphate glasses. Next, continuation of the borophosphate glasses and evidence of mixed alkali effect. Mixed alkali effect means we are taking the mixed alkali elements, lithium, sodium, potassium, rubidium, cesium. These are the alkali elements. Whenever mixed alkali elements, one or more than two. So that means the mixed alkali effect means MA is one of the most exceptional but poorly understood phenomena in glasses and glass science. It has been observed quite generally in alkali modified network oxide glasses that the substitution of alkali by another at a total fixed concentration of the alkali gives rise to nonlinear variation of properties exhibiting minima or maxima. So whenever you are adding with a mixed alkali elements, Suppose for example lithium oxide, potassium oxide, or cesium oxide, or sodium oxide. This kind of mixed alkali elements we are whenever doping in borophosphate classes. At that time, the mixing concentration of the minimum and maximum should be uniform. That means we are varying the concentration of the alkali elements. So lithium, suppose total concentration is 30%, means we can vary the lithium and potassium 5, 25, 10, 20, like that we have to change the concentration of the mixed alkali elements, that is lithium, potassium. So other one is the nonlinear behavior of the certain properties with respect to alkali content is known as the mixed alkali effect. That means the nonlinear behavior of certain properties with respect to alkali content is known as the mixed alkali effect. So various thermodynamic analysis have been given to explain the mixed alkali effect. So other some various thermodynamic analysis have been given to explain the mixed alkali effect in the case of borophosphate classes. This effect has significant applications and makes the mixed alkali classes of special interest. For instance, low dielectric loss. So low dielectric loss classes can easily be obtained by incorporating two different alkalis. Suppose lithium, potassium, otherwise lithium, cesium, or lithium, rubidium, or lithium, sodium. This kind of nature, that is a mixed alkali effect. So easily be obtained by incorporating the two different alkali ions. This is most notable in properties related to alkali ion transport. So this is the notable property in the case of mixed alkali effect. So alkali element changing the variation of the alkali elements. So that is the mixed alkali effect. This is the an evidence of mixed alkali effect in borophosphate classes. Next is material selection. The present material selection highlights the facts advantages behind the selection of borophosphate class system for present study. In this study, we have studied the borophosphate classes. So that borophosphate class mainly they study on the EPR, that means electron paramagnetic resonance, and photoluminescence studies on lithium, potassium, borophosphate classes doped with magnesium 2 plus ion. So here transition metal ions we are used is Mn 2 plus ions. So in this study we are using the chemical composition of Mn 2 plus doped borophosphate class system. So here we are taking the lithium oxide. This is the alkali content. Other one is potassium oxide, K2O. So lithium oxide and potassium oxide, these are the alkali elements. Then we are also adding the borate and phosphate, that means borophosphate. So 35% of mole percentage of B2O3 and 34.5% of P2O3, and only less concentration 0.5 mole percentage of magnesium oxide, that is MnO2. That means that is why we get in Mn2 plus test. So MnO2 magnesium oxide. So Mn2 plus, that is we are doping with transition metal ions in the borophosphate. So that concentration, the lithium content and potassium content, these are the mixed alkali elements. So that elements we are varying the that concentration from 5 mole percentage to 25 mole percentage. So here see the x 5, 30 minus x means 25. So 5, 25. Next 10, 20. Here 15, 15. 10, 25. Next year 25, here 5. Like that we are varying the lithium and potassium concentration. In the case, then we can say lithium, potassium, borophosphate classes doped with Mn2 plus ions. So total concentration should be 100 mole percentage. Total should be 100 mole percentage. So here 30% of alkali content, remaining 70% borate, phosphate, and 0.5% of MnO2. That is a low concentration of magnesium dioxide, MnO2. So that is EPR and luminescence properties of Mn2 plus doped borophosphate glass. So we can say lithium, potassium, borophosphate glass doped with Mn2 plus ions. Next, coming to the experimental technique or preparation of glasses. So preparation of the glasses prepared by using the melt quenching technique. That method or technique is called the melt quenching technique. Melt quenching technique is nothing but whenever using the high temperature to suddenly keep down to the room temperature. That is called melt quenching technique. So we are keeping the temperature in high temperature. Suppose, for example, 1000 degrees centigrade for in the case of Boro phosphate glasses, after cool down to room temperature. So that kind of study is called as technique or method is called as a melt quenching technique. So first initially the above compositions. So in this study we are using lithium oxide, potassium oxide, boron trioxide, phosphorus pentoxide P2, and dopant is manganese dioxide. So this glass composition weighing as per this chemical composition we are taking the weighing in the grams of 8 to 25 grams. Each batch glasses we can preparing 8 to 25 grams. So as per the chemical composition, we are taking the chemical composition by using the optical balance. We are weighing the each and every chemical. After taking the that weight, we can pour into the platinum crucible. Here, this is platinum crucible. In this platinum crucible, we pour the weighed chemicals in that platinum crucible. After that, we can keep into the electrical furnace at the temperature, melting temperature of 1000 degrees centigrade. This is only for the borophosphates. Our duration time is 30 minutes only. So we are keeping that chemical composition into the electrical furnace at the temperature of 1000 degrees centigrade for 30 minutes duration. After melting the chemical composition, this is solid chemical is converted into the liquid type. After liquid pouring we can pour into the preheated brass mold. This is the preheated brass mold. So we are keeping after pouring into the that chemical liquid into the brass mold, we are keeping at the annealing temperature at 350 degrees centigrade. That is, annealing is mainly used for the to avoid the thermal stress and strain. So that is mainly this annealing temperature. We have to select the below the glass transition temperature of the borophosphates. So in the present glass, what is the glass transition temperature? So if your glass temperature is 380 or 400 degrees centigrade, we have to choose the below the that temperature. So in this borophosphates, we choose the annealing temperature is 350 degrees centigrade. Melting temperature is 1000 degrees centigrade. Duration time is 30 minutes. So after glass preparation of the completion of the glass preparation, we can cut the glass pieces, small pieces as per your requirement. Then we can polish the each and every glass sample. Then we can send into different kind of measurements. So first we have to measure the XRT profile. So we are prepared a glass sample is shows the glassy nature or crystalline nature. We have to whether confirm the that glassy nature or crystalline nature by using the XRT profile. After measurement of XRT profile, we confirm that the prepared glass sample is looks like a glassy nature. Whenever you are getting the broad peaks, so XRT profile 2 theta versus intensity we are measuring. So in this one we are observing the graph curve should be shows the broad peaks only, not sharp peaks. That means it shows the crystalline nature. You cannot get anything. That is why you are getting glassy nature. Broad peaks shows the glassy nature. So finally, we are confirmed that. So our prepared samples are the completely glassy nature. So after getting the glassy nature, we can measure the different kind of characteristics in the present study. So experimental technique and methods are characterization types. So first, you need to measure the EPR spectra, electron paramagnetic resonance spectra. In this spectra, you can study the site symmetry, and the same way we know the outermost orbital vacancy level. We can study the by using the EPR spectra. So used instrument is the electron paramagnetic resonance spectra of a sample were taken on dual Fe1x ESR spectrometer operating in the X-band frequency 8.8 to 9.6 GHz with a field modulation of 100 kHz. So this is the instrument for ESR spectrometer, X-band ESR spectrometer. You can measure the EPR spectra analysis. Then absorption spectra. So in Petri-Nellman spectrometer, we can use the wavelength range of 250 nanometer to 2500 nanometer. Next, fluorescence measurements. So luminescence measurements we can measure by using the Jobin ion fluorolog 3 spectrophlorimeter using xenon arc lamp as a radiation source. Here, xenon arc lamp as a radiation source while measuring the fluorescence measurements. So in this spectrometer, we can use to measure the excitation spectra as well as emission spectra, fluorescence spectra. So these are the characteristic technique of the present study. EPR analysis and absorption and fluorescence analysis. So coming to the first results and discussion, we can study the first analysis is EPR analysis, electron paramagnetic resonance. In this analysis, we can get the graph. The first graph shows the EPR spectra of 0.1 mole percent of MnO2 doped with lithium, potassium, boro phosphate gas at room temperature. So here you can study the magnetic field versus first derivative absorption curve. So in this, it starts from the magnetic gas. Here, the expand the ESR spectrometer, we can fix the microwave frequency at 9.6 gigahertz. We can tune the magnetic field gases from 2200 gas to 4200 gas. So this different kind of alkali content X equal to 5. This is alkali content concentration. Lithium 5 mole and 10 mole, 15 mole. Remaining potassium is 25 here. That means X10, next X15. These are the lithium concentration. So in this graph shows the, we can get the resonance signal of the ESR spectra from the Mn2 plus doped lithium, potassium, boro phosphate. We are getting the 6 lines, 6 peaks, sharp peaks, 1, 2, 3, 4, 5, 6. So 6 peaks you are getting. 6 resonance peaks. That is mainly due to the 2I plus 1. That is it. The spin of the Mn2 plus ion. The resonance signal we are getting the each and every spectra shows the 6 hyperpen structures. Hyperpen structure mainly due to the nuclear spin of the Mn2 plus ions. So here nuclear spin of Mn2 plus ion is equal to 5 by 2. That means I equal to 5 by 2. That means 5 plus 1, 6. So finally we are getting, as per the nuclear spin 2A plus 1 rule, that we are getting the, so hyperpen structure is in magnesium, gives the beautiful resonance signal of the 6 lines of the hyperpen structure at the resonance factor, Landau splitting factor G value at G equal 2.02. This is due to the attribution of Mn2 plus ions present in the lithium, potassium, boro phosphate classes at room temperature. Next figure shows this figure shows the EPR spectra of lithium, potassium, boro phosphate doped with Mn2 plus ion at different temperature, from room temperature to at low temperature. Here using the liquid nitrogen as the, to decrease the temperature from room temperature to low temperature, we are using in the ESR spectrometer liquid nitrogen. So that is why you can cool down the temperature from room temperature to low temperature 123 Kelvin. So here different kind of temperature we can measure the resonance signal of the ESR signal. So in this case also we are getting the same G factor, Landau splitting factor resonance signal G value equal 2.02. This also due to the presence of Mn2 plus ions present in the lithium, potassium, boro phosphate classes at different temperatures. So this is the ESR analysis. Next, coming to the EPR spectra at room temperature and different temperature. So from EPR analysis, when Mn2 plus ions were introduced in the lithium, potassium, boro phosphate classes, the EPR spectra of all the investigated sample Mn2 plus ions exhibit the resonance signal with the effective G value G equal 2.0 with a 6-line hyperpen structure, which I discussed with the 6-line hyperpen structure. That is mainly due to the nuclear spin of the Mn2 plus ions is 5 by 2. That is why you can get the 2A plus 1. So you can get the 6 lines of the hyperpen structure. That is mainly due to the Mn2 plus ions presence in the lithium, potassium, boro phosphate. This hyperpen structure, HFS means hyperpen structure, due to the interaction of electron spin of manganese ions with its own nuclear spin, I equal 5 by 2. That is why you are getting the 6 lines of the hyperpenization, because its nuclear spin, own nuclear spin of the manganese ions is I equal 5 by 2. So as per the 2A plus 1, you can get the 6 lines of the 6 lines of the hyperpen structures in the Mn2 plus doped lithium, potassium, boro phosphate classes. So this figure shows the EPR spectra of the glass sample observed at room temperature for different composition of glasses. So that we are shown in this diagram. Next, coming to the EPR spectra of lithium, potassium, boro phosphate glass sample recorded at a low temperature, from temperature varying from 123 Kelvin to 295 Kelvin. And I have been shown in the figure. The number of spins participating in resonance signal G equal 2.02 have been calculated at various temperature. And also we can calculate by using the EPR analysis, we can calculate the number of spins participating in the resonance signal at Landau splitting factor G equal 2.02. that we are calculating by using the standard formula of the number of spins participating in the resonance signal in the case of Mn2 plus doped lithium, potassium, borophosphate gases. This is the formula for the calculate the number of spins participating in the resonance. See, number of spins participating in the resonance can be calculated by comparing the area under the absorption curve. So, in this spectra, the area under the absorption curve. So, here giving the y-axis is first derivative of absorption peaks. These are the absorption peaks of the ESR signal. So, each and every peaks, you have to calculate the area under the absorption curve. So, you have to calculate the area by using this formula. So, AX is the area, A means, X means sample, and STD, standard means that is the reference value, copper sulfate 5H2 in this study of known concentration. So, here given sample concentration means Mn2 plus ions, standard composition is copper sulfate 5H2. So, both we are comparing and using this formula, we can calculate the number of spins participating in the resonance. So, by using this formula, we can calculate the number of spins N value. So, by using the N value, we can calculate the different kind of parameters. So, here variation of number of spins with alkali content. Here we are changing the variation in the alkali content from 5 mole concentration to 10 mole, 15 mole, 20 mole, 25 mole. So, here x-axis concentration of the alkali content, in y-axis number of spins, n into 10 power of 22 ions. So, that is number of spins. How many spins is participating in the Mn2 plus ions in the lithium, potassium, borophosphate gases. This variation may be due to the structural changes with the composition and also the modification of boron network. Because we are using the B2O3 boron trioxide. That boron network with alkali content, and also you are additionally you are added with alkali content, lithium oxide as well as potassium oxide. So that is the structural changes with the composition and also modification of the boron network with alkali content. So this we can study by using the variation of number of spins. Next, by using the EPR resonance signal only, you can calculate the activation energy. At the same time, paramagnetic Curie temperature also you can calculate by using the EPR signals and also number of spins participating in the resonance signal. So this in first figure shows the x-axis 1 by T, the temperature Kelvin. So 1 by T versus log N. Log N means number of spins participating in the resonance. That is log N you are taking, and you can linear fit. We can fit it with this data points in linear fit. Log N equal to 17.80 plus 60.480 by T. So by using the linear fit equation, we can calculate the activation energy of the Mn2 plus ion. This activation energy in Mn2 plus ions is 0.119 electron volt of the activation energy in the case of lithium, potassium, borophosphate classes. At the same way, in the second figure shows the temperature versus susceptibility, the 1 by psi, that is susceptibility. So N is the number of spins, G is the random splitting factor, beta is the Bohr magnet, and J is the quantum number, Kb is the Boltzmann constant, T is the absolute temperature, T Kelvin. So by using this formula, susceptibility we can calculate. By using the susceptibility, we can calculate the paramagnetic Curie temperature. So by using this formula, we can calculate the Curie temperature at theta T equal 90 Kelvin. So these are activation energy and a paramagnetic Curie temperature. Both we are going to study in the by using the number of spins and also EPR signal, electron parameter resonance signal. And the Curie constant C also you getting 0.592 EMU per mole. These are the important parameters. While measuring the EPR signal, we can study this analysis: activation energy, paramagnetic Curie temperature, Curie constants, Curie constant. So next we are going to study the excitation and emission spectra of the lithium, potassium, borophosphate gases doped with Mn2 plus ions. So in the first excitation spectra, in the first figure shows the excitation spectra. This wavelength versus normalized intensity. So wavelength from 300 nanometer to 500 nanometer, we can observe the through two broad, one broad peak and one more also broad peak, but little intense. So that is so excitation peaks from ground state to different kind of excited states of Mn2 plus ions. In the case of here, Mn2 plus ions, the lithium, potassium, borophosphate doped with Mn2 plus ions. So in this gas composition, the Mn2 plus shows it exhibit the two excitation levels from the ground state. So from the ground state, excited state levels is quadrate EGD and quadrate A1GEG and quadrate EGG. Whenever emission you are getting 582 nanometer. So here in the excitation spectra, you are keeping emission is the excitation source. Then you are getting the two excitation peaks from ground state to different kind of excited states. That in case of Mn2 plus ions. So that is the first figure shows the excitation spectra. Second one shows the emission spectra. In this emission spectra, wavelength versus normal intensity only. Whenever exciting with 410 nanometer. So lambda excitation is 410 nanometer. We can get the 582 lambda. That is emission is 582. This broad emission. That is a green emission 582 nanometer. That is attributed to the doublet T1GG2 6A1GS. This is the transition of the emission band of the Mn2 plus ions. That is this Mn2 plus doped lithium potassium Boro phosphate ligases exhibit the green emission. So we can use for the green laser applications also. We can use for the lithium Boro phosphate ligases doped with Mn2 plus ions. So we can use for the laser applications as a green laser applications. We can use it because we can get the broad band at the wavelength region of 582 nanometer whenever exciting with 410 nanometer of the excitation pump source. So these are the excitation and emission spectra of the lithium potassium borophosphate classes doped with Mn2 plus ions. Next, coming to the excitation and emission spectra, this analysis and discussion. The excitation spectra of Mn2 plus doped lithium potassium borophosphate class sample has been studied at room temperature and been shown in the figure. So these are the excitation spectra and emission spectra. So the excitation spectra exhibit two bands centered at 356 nanometer. That energy is 28,090 centimeter units of energy, and the other band is 410 nanometer, 24,390 centimeter. So in these two excitations, see here in this diagram, so you are getting two emissions. One is 3, one is 356, other one is 410. So compared to the 356, this is 356, this is 410 nanometers. We can get through excitation wavelengths. First one is 35 lower level, that means higher energy 356 nanometer and the 410 nanometer. So this one is the excitation level is higher intensity is 410 nanometer. So that is why which excitation peak we are getting the intense peak. So in the case of in the two peaks, we can get the 410 nanometer is the pumping energy will be more. That is the intensity will be more. That is why you can choose the for emission spectra analysis pumping source. We can use the 410 nanometer while taking from the excitation spectra, because in 356 we can get the less intensity. This one less intensity compared to 410 nanometer. So we can get the excitation is 410 nanometer is high intensity. That is why you are choosing the excitation source for emission spectra analysis. We can use the 410 nanometer of the excitation wavelength for pumping purpose. We are choosing the for emission analysis, emission spectra analysis. That is why we are using the 410 nanometer. We are getting the emission band at 582 nanometers that we are studying here. So this is the we have been attributed to the transition from the multiplets of quadrate TEGD to quadrate A1GG and quadrate TEGG respectively. The ground state of the 6A1G6S of the Mn2 plus ions. These are the ground state of the Mn2 plus ions. These are the different excitation wavelength energy levels. So next is emission level spectrum. So the emission spectra of lithium potassium borophosphate classes sample recorded at room temperature exhibit green emission 582 nanometer. That energy is 17,180 centimeter inverse. They are exciting with 410 nanometers shown in the figure. Therefore, the green emission line at 582 nanometer in the lithium potassium borophosphate classes is assigned to the transition upper level quadrate 1G to the ground state level 6A1G state of Mn2 plus ions. So this is the broad emission at 582 nanometer. This is the belongs to green emission region. That is why this kind of glass material you can use for the green laser applications. So these are the one of the important application in the green laser application we can use for the Mn2 plus dope borophosphate classes. So finally we conclude that The EPR spectra of Mn2 plus ions in lithium potassium borophosphate classes exhibit a resonance signal with effective G value at G equal 2.02 with 6-line alpha structure. That is mainly due to the nuclear spin of the Mn2 plus ions I equal 5/2, that is by 2A plus 1. We can get the 6 lines of alpha structure in the case of Mn2 plus doped lithium potassium borophosphate. The resolved hyperpine structure indicates the paramagnetic ions in the divalent state, and the site symmetry is distorted octahedral site. So, the EPR signal, we can study this unique technique. EPR is one of the unique technique to study the site symmetry of the dopant ions. That means here used dopant ion is Mn2 plus ions. So say Mn2 plus ions belongs to the site symmetry is distorted octahedral symmetry. That we are going to study by using the Landau splitting factor G equal 2.02. By using this value, we can calculate this site symmetry is belongs to the disorder octahedral symmetry. Next, the population of spin levels N exhibit a nonlinear behavior with the composition of the class indicates the mixed alkali effect of lithium, potassium, borophosphate. That means nonlinear behavior means in the case of C here, first initially low concentration it increases. Maximum 10 mole concentration of lithium content, then decreases. Again at the 25 mole percentage of lithium concentration increases. So low, minimum, maximum, minimum, maximum. So this kind of behavior shows the mixed alkali effect in the case of alkali elements whenever added in the borophosphate classes. That we are going to study the mixed alkali effect. So the behavior with the composition in the classes indicate the mixed alkali effect in the lithium, potassium, borophosphate classes. The photoluminescence spectra exhibit green emission peak, which is attributed to a transition from the excited state quoted T1G to the ground state 6A1G state of Mn2 plus ions. So this is the we can get the from emission spectra green emission at wavelength of 582 nanometer. That is the green emission wavelength. So that is used for the green laser applications. We can use for the Mn2 plus dope, lithium, potassium, borophosphate classes. These are the summary and conclusion of the present study. Next, references. These references are used in the present study. The last reference is the one of reference for the myself only. So in this paper, we can discuss the EPR and photoluminescence properties of the Mn2 plus dope borophosphate classes. Borophosphate means in the case of here using mixed alkali elements is lithium and potassium. So these are the references belongs to the present study. Next, thank you. Next section to be continued in the other chapter.
Like, share and subscribe. Hit the bell icon for more updates.